Hello everyone, in this new episode of our discussion on organic chemistry, the basic concepts, we will discuss reaction intermediates. There are several reaction intermediates which are formed during a reaction, very short-lived and mostly non-isolable forms. That is when a set of reactants are converted to products. You have in between very short-lived, highly reactive, highly unstable species called reaction intermediates. Being highly unstable and highly reactive, they are quickly converted into products, the more stable form called products. And there are different types of reaction intermediates like carbocations, carbanions, free radicals, carbenes, nitrines, arynes, etc. But in this discussion, we will focus on carbocations, carbanions, and free radicals. We will shortly see the structural stability aspects of these three free radicals. Coming to carbocations, these are organic species, cationic species where positive charge is present on carbon atoms. Two types of carbocations, carbenium ions and carbonium ions. Carbenium ions are trivalent carbon species like methyl carbocation where carbon is trivalent and the fourth valency is lacking with the positive charge. Whereas carbonium ions are also called non-classical carbocations. They possess pentavalent carbon and this pentavalent carbon possesses the positive charge. And carbocations are sp2 hybrid ones, that is the carbon atom bearing positive charge is sp2 hybridized with the shape of trigonal planar structure, that is the carbon bearing the positive charge undergo sp2 hybridization and the three hybrid orbitals lie at the corners of a trigonal, the planar trigonal shape, and these three lobes or these three hybrid orbitals are overlapped by 1s orbitals of hydrogen atom like this, and then there is an unhybrid vacant p orbital lying in the perpendicular plane to the triangle. So this is the structure of carbocation involving the sp2 hybrid central carbon atom which is bearing the positive charge. Let's see the structural stability of carbocations varying from tertiary, secondary, primary and methyl carbocations. Tertiary carbocation has got three substitution with alkyl groups like this, and secondary possesses two alkyl groups, and primary possesses only one alkyl group substitution, and methyl carbocation is completely unsubstituted. That is, all the three valencies of carbon are satisfied by hydrogen atoms. And how do we explain the stability of these four different species, the relative stability? Here we can apply the idea of two electron displacement effects, that is inductive effect and hyperconjugation. Let's see how inductive effect work here. In one of the previous lectures, we have seen inductive effect and how to explain the stability of different species by using the concept of inductive effect. If not, please revisit that particular session in the same series. Methyl groups are plus I groups, that is positive inductive effect groups. They are releasing electrons away from it. Therefore, in the tertiary carbocation, there are three methyl groups with positive inductive effect, that is they are releasing electrons towards the charge bearing carbon. Therefore, as this carbon receives more and more electron density from the alkyl group, its charge is stabilized. Magnitude of the positive charge decreases, therefore the carbon charge is stabilized here. As you've got lower number of alkyl groups, this carbon, the charge bearing carbon, experiences less inductive effect from this methyl group, attached methyl group, and therefore the stabilization decreases as you go to secondary, and it further decreases as you go to primary, and in the methyl carbocation you cannot see any degree of inductive effect because there is no alkyl group at all. So the stability of carbocations vary in this order, that tertiary carbocation is more stable than secondary, which is even more stable than the primary, and methyl group is the least stable among this category. And another idea you can use is hyperconjugation here. If you look at this tertiary carbocation, there are 9 alpha hydrogens in total arising from the 3 alkyl groups, 3 methyl groups, and you can see that these alpha hydrogens, the respective CH bonds can be in resonance with the carbon bearing the positive charge. There is an empty p orbital and hybrid p orbital, if you remember the structure. Therefore, 9 non-bond resonances are possible here for the tertiary carbocation. Whereas for secondary, there are only 6 alpha hydrogens, 6 resonance structures are only possible. Whereas for primary, here only 3 alpha hydrogens and the number of hyperconjugated structures is 3. Whereas for the methyl ones, there is no alpha hydrogens. Therefore, as the number of alpha hydrogens decreases, the extent of hyperconjugation decreases, therefore extent of stabilization decreases. Again, based on the idea of hyperconjugation, you can say that the carbocation stability follows this order. That's about carbocations, and let's now move on to carbanions. Carbanions are similar reaction intermediate but with a negative charge on one of the carbon atoms. And the charge bearing carbon is sp3 hybridized. Sp3 hybridization gives 4 sp3 hybrid orbitals like here, which are aligned in the corners of a regular tetrahedron. Theoretically, that's what we expect. On the 3 lobes of this sp3 hybrid orbitals, 1s orbital of hydrogens get overlapped, and on the 4th orbital you have a pair of electrons, lone pair of electrons there, giving rise to the negative charge. And due to this lone pair repulsion with the other bond pairs, the structure gets distorted from the tetrahedral form to a pyramidal structure. So carbanions are having pyramidal structure. Coming to the stability, as we have seen for carbocations, we can explain the stability of carbanions too with the help of inductive effect. Due to the positive inductive effect of methyl groups, it can release electron pairs towards this charge-bearing carbon, but this time the inductive effect of the alkyl group increases the charge magnitude on this particular carbon in the middle here. Therefore, the charge the carbon atom in the middle become highly destabilized. Whereas if you go to the secondary carbanion, you have only 2 alkyl groups. Therefore, the magnitude of inductive effect decreases, and for primary decreases further. And if you look at the methyl group, there is no plus I group. That means there is no charge destabilization. Therefore, stability of carbanions follows this order, where the tertiary carbanion is least stabilized, whereas methyl carbanion is the most stable among the set. And now we move on to free radicals. Free radicals are neutral species containing unpaired electrons. The free electron bearing carbon is sp2 hybridized, resulting into a trigonal planar structure like this. And as we've seen before, the hydrogens, 1s orbital of the hydrogens overlap here, and there is an hybrid p orbital which occupies the unpaired electron, which gives the species a free radical nature. And this is the structure, and the stability can be explained based on hyperconjugation, because in the first structure there is a tertiary free radical, as we have seen before. 9 alpha hydrogens possible, therefore 9 no bond resonance structures can be obtained, whereas for secondary there are only 6 alpha hydrogens, therefore 6 no bond resonance structures, and for primary only 3 alpha hydrogens, 3 hyperconjugated structures, and for the methyl free radical there are no alpha hydrogens, no hyperconjugation at all. So we know from our discussion on hyperconjugation there, as the number of hyperconjugated structure increases, the species will be stabilized. Therefore, the tertiary free radical is the most stable in this set, whereas methyl radical is the least stable one. Okay, with that we are coming to end this discussion on basic concepts in organic chemistry, and I'm looking forward for your feedback, and thank you for sticking on to the series. Thank you.